Hi there, my name is Avinash Bhatt and I'm a process engineer at Evoco Water Technologies. This presentation, Ultra Low Total Phosphorus, A Tale of Three Cities, is the story of pilot testing of a magnetite ballasted technology called COMAG at 3 Wisconsin cities. Before I begin, let's take a brief tour of the presentation. I will attempt to answer the questions why, where, what, and how. First, I will be taking a step back and explaining the regulatory reasons that required the 3 cities I'm going to talk about to explore low phosphorus technologies. Next, we will see where the plants are located. After that, I will spend a few minutes explaining the technology that was used. Finally, we'll take a look at the results of the pilot tests, the most interesting aspect of this presentation. First of all, a little bit of background on why wastewater treatment plants in Wisconsin started looking at low phosphorus technologies. As you might expect, the story begins at the Wisconsin state capitol in Madison. Revisions to Wisconsin's phosphorus water quality standards for surface waters were adopted on December 1, 2010. State Statute NR 102 sets maximum thresholds for phosphorus in surface waters. NR 217 set procedures to implement NR 102 phosphorus standards in WPDES permits issued to point sources. At the same time, NR 151 tightens agricultural standards for phosphorus. Municipalities started evaluating technology options to meet new phosphorus limits proposed. After shortlisting technologies, municipalities chose to pilot some, ballasted settling being one of them. Following the changes to NR 217, several large Wisconsin municipalities started evaluating ballasted technologies to address potentially new total phosphorus limits. The 3 cities we are going to talk about today are Fond du Lac, Waukesha, and Madison. At Fond du Lac, the pilot was run at the Fond du Lac Water Pollution Control Plant. At Waukesha, it was run at the Waukesha Clean Water Plant. And at Madison, the pilot was run at the Madison Metropolitan Sewage District's 9 Springs wastewater treatment plant. Next, we'll take a look at the process itself. The process starts with the addition of coagulant upstream of the first tank, the coagulation tank. The coagulation tank provides residence time for the formation of chemical flocks from the addition of coagulants upstream. Generally, this tank has a hydraulic retention time of about 6 minutes. The coagulant is shown here as aluminum or ferric ions. From the coagulation tank, water flows to the ballast tank. As you may have guessed from the name, ballast is introduced in this tank. As I mentioned before, this process uses magnetite as ballast material and is introduced either manually or mechanically directly into this tank. This tank has 2 other sources of magnetite, which we'll take a look at in a bit. Mixing energy provided in this tank ensures that the ballast gets embedded in the chemical flock as opposed to remaining free in the bulk fluid. It is also worth noting that this is where the process diverges from a conventional tertiary coagulation flocculation process. The addition of ballast makes the sludge settle faster in the clarifier further downstream. From the ballast addition tank, water flows to the last tank in the series, the polymer tank. Again, as the name suggests, a polyelectrolyte or polymer solution is introduced here. The polymer solution further enhances the flock structure, helping the sludge settle even more efficiently in the clarifier that follows this tank. The hydraulic retention time in this tank is also 3 minutes. Thus far, the 3 tanks in series have had a hydraulic retention time of 6 minutes in coagulation, plus 3 minutes in ballast, and finally 3 minutes in polymer, for a total of 12 minutes in all tanks. Water flows from the coagulation tank to the tertiary clarifier or sedimentation tank. The clarifier is the final step in the treatment train. The COMAC process can use either a conventional clarifier or one with inclined plates or inclined tubes. All the 3 pilots in Wisconsin were run with a conventional clarifier. An important point to note here is that in a ballasted process, the clarifier can be up to 10 times smaller than one in a conventional process. As we'll see a little bit later on, the surface overflow rate, or SOR, through a high-rate ballasted process such as this is generally about 10 times higher than the SOR through a conventional clarifier, which results in a much smaller clarifier. The effluent from the clarifier is conveyed usually to disinfection before final discharge. Before we go further, we go back to the clarifier for a few more moments, specifically to the underflow from the clarifier. Sludge withdrawn from the clarifier is pumped in 2 directions. The first is recycle, whereby a fraction of the clarifier underflow sludge is pumped back to the ballast tank, a process that is not that dissimilar from return activated sludge pumping in an activated sludge plant. Recycling solids in this manner recirculates solids, creating a higher solids concentration in the ballast tank. Remember, I mentioned 3 sources of magnetite in the ballast tank earlier. Sludge recycling is the second source of magnetite. A secondary effect of sludge recycling is that any unused chemical has a chance to get pumped back into the process and get used up completely, making the process more efficient. Most COMAC magnetite ballasted systems are designed to recycle up to 5% of the influent flow rate. The second direction where sludge is pumped is the wasting system. Again, not that dissimilar from an activated sludge plant. Chemical solids formed in the process have to be removed or wasted from the system. The waste sludge is pumped to the ballast recovery system to separate waste sludge from the ballast. The ballast recovery equipment recovers more than 99% of the magnetite, which flows by gravity to the ballast tank. This is the third source of magnetite to the ballast tank. Chemical sludge that is separated from the ballast recovery equipment is sent further downstream to the wastewater treatment plant's sludge handling process. Next, we'll take a look at some characteristics of the ballast itself. So after having had a look at the process itself, let's take a look at the ballast material that's used in this process. Magnetite, as I mentioned before, is used as ballast. So why use magnetite as ballast? Well, the best reason is that it's heavy with a specific gravity of 5.2. It is readily available with almost every continent having abundant resources of magnetite. Plants in North America have used magnetite from South America, North America, and Europe. There are suppliers in South Africa and Australia that have provided magnetite. The point is, it's a readily available material. It is inexpensive, as low as about 30 cents a pound in most places in the United States. The material is inert. Magnetite is used in drinking water plants and has an NSF certification. In fact, one can even ingest it without any ill effects, other than bad taste, of course. Since it's completely oxidized, it does not react with other substances generally found in a water treatment plant. An important characteristic of any ballast material that is often overlooked is ease of conveyance. To use the ballast effectively, one should be able to convey the material from its bulk storage location to the point of use. Magnetite can be conveyed by mechanical means or pneumatically. Mechanically, it can be conveyed dry or in slurry form. For pneumatic delivery, it must be in dry form. Finally, a ballast material must be recoverable to a high degree, which magnetite is. In tertiary applications, for example, more than 99% of magnetite is recovered. Now let's take a look at the total phosphorus results from the 3 pilot tests. First up, Fond du Lac. This graph shows test values for the entirety of the pilot test period, including stress tests. On the x-axis is time of day, and on the y-axis is the total phosphorus concentration. The y-axis is on a log scale. As you may have already guessed from the values, the red points are influent total phosphorus concentrations and the green points are effluent concentrations. These concentration values were measured from both grab as well as composite samples. For simplicity, I have chosen not to distinguish the two types of samples. The dashed lines show target effluent total phosphorus concentrations for each day of the pilot test. The Fond du Lac test was run in September and October 2013. The target effluent total phosphorus concentration was 0.04 milligram per liter in anticipation of getting a monthly average effluent permit limit around that concentration. 3 coagulants were tested: ferric, alum, and polyaluminum chloride. All coagulants could meet the 0.04 milligram per liter effluent total phosphorus target. On the 24th of September, 1st of October, and the 11th of October, hydraulic and solid stress tests were run, which is evident from a sudden increase in influent total phosphorus concentrations during those days. We'll take a more detailed look at stress test results in a few minutes. Along the same lines as Fond du Lac, shown here are the Madison pilot results. Ferric chloride was the only coagulant tested here. The effluent total phosphorus goal at Madison wasn't as low as at Fond du Lac. The aim was to get below 0.075 milligram per liter effluent total phosphorus at the steady state condition. Hydraulic stress tests to simulate a storm flow condition and solid stress tests to simulate a secondary clarifier upset condition were run on the 10th and 12th of October. It is to be noted that the influent total phosphorus concentrations at Madison were lower than at Fond du Lac. The Madison pilot was run in October 2018. Finally, this is an overview of the Waukesha pilot. As at Madison, ferric chloride was the only coagulant tested here. The pilot aimed to target 2 effluent total phosphorus concentrations, 0.028 milligram per liter and 0.042 milligram per liter, both of which were met. Tests on the 19th and 20th of June were conducted to get below 0.028 milligram per liter effluent total phosphorus concentration. On June 8th, the target was 0.03 milligram per liter. As you can see from the last group of points, the average effluent total phosphorus concentration was comfortably below the target. While doing this low total phosphorus test, the SOR was also raised by about 114% compared to the other test days. We shall look at hydraulic stress tests in more detail in a few moments. As I mentioned earlier, let's take a closer look at stress tests, starting with solid stress tests. I would like to graphically show the results of the stress test by adding data in layers so that it is easier to understand the graph in its entirety. The x-axis shows the influent and effluent sample points. The y-axis shows the TSS concentration on a log scale because of the large variation of influent TSS to the system during these tests. The first set of points shown in yellow are influent and effluent TSS concentrations during the regular non-stress test period. Next shown are influent and effluent TSS concentrations during the stress test period. The red points are Fond du Lac tests, while green ones are Madison points. As you can see, the TSS concentrations during the stress tests were considerably higher. At Fond du Lac, for example, averaging higher than 100 milligrams per liter. The stress test influent concentrations are joined by a straight line to the corresponding effluent concentrations to gauge whether higher effluent TSS concentrations were observed when influent concentrations were high. As you can see from the fact that the lines cross, higher influent TSS did not correspond to higher effluent TSS. A final layer added to the graph is a box plot to show the distribution of concentrations during the stress test. The median influent TSS concentration at Madison and Fond du Lac were close to 100 milligram per liter. What's interesting is that the effluent TSS box plot for the regular test almost completely overlaps the box plot for the stress test, and the median TSS concentration during the stress test was lower than during the regular test. Similar to the TSS stress test, shown here are the results of the total phosphorus stress test. The influent TP concentration at Fond du Lac was allowed to go up to almost 3 milligrams per liter, and the effluent performance did not suffer. What one can see clearly is that even when the influent total phosphorus concentration was close to 3 milligrams per liter, the total phosphorus concentration at the effluent was often 2 orders of magnitude lower. The effluent goal at Madison was higher than at Fond du Lac, which is why you see effluent concentrations higher there during the stress test. A change in coagulant feed rate essentially produced the desired effluent total phosphorus concentration. The stress tests were generally run for an entire 6 or 8 hour period during the day to ensure that the system was stable. For a high rate system such as this, a 6 hour period is like running an average condition and is more than adequate to demonstrate system stability, because during a 6 hour period, the system goes through almost 30 hydraulic retention time periods. After taking a look at the solids stress test results, let's take a look at the hydraulic stress test results. On the x-axis is shown the clarifier surface overflow rate in gallons per minute per square foot. On the y-axis is shown the effluent total phosphorus concentration in milligrams per liter. To start with, what are we comparing the system SOR against? The gray bar indicates the range of SOR values for a conventional system, generally between 0.6 and 0.8 GPM per square foot. The points in red show the SOR values during the tests at Fond du Lac. A majority of the tests were conducted at about 5 times the conventional SOR, or about 3 GPM per square foot. During the hydraulic stress test, the average SOR was increased to up to 6 GPM per square foot, about 10 times the conventional SOR. Green points are the SOR values at Madison. At Madison, we started at 6.5 GPM per square foot, which was increased to 8 GPM per square foot during the hydraulic stress test. Blue points show the SOR values at Waukesha, where the SOR tested was even higher. As you can see, the pilot was tested at more than 20 times the conventional SOR while meeting an effluent total phosphorus concentration of less than 0.05 milligram per liter. From a plot of SOR against effluent total phosphorus, it is evident that there is no relationship between effluent total phosphorus and the SOR for the range of SOR values tested. The statement is true for all 3 pilots combined, as well as each pilot in isolation. In almost all cases, to achieve a low effluent total phosphorus concentration, adjusting the coagulant dosage was key. The final set of data we are going to look at is coagulant performance. This graph shows the performance of the 3 coagulants at Fond du Lac, the only site where the 3 were tested. The coagulants are shown on the x-axis and the effluent total phosphorus concentration is shown on the y-axis. The y-axis is on a log scale to better show the difference in coagulant performance. The mean effluent total phosphorus concentration is shown by text boxes next to each box plot. Looking at the distribution of effluent total phosphorus values, one can see that the effluent total phosphorus concentrations were on average higher when using alum and polyaluminum chloride coagulants. Both are aluminum-based coagulants, so similar performance vis-a-vis total phosphorus removal is not surprising. A one-way ANOVA test to compare the effect of coagulant on effluent total phosphorus shows that there is a significant effect of coagulant type on the mean effluent total phosphorus concentration at the 95% confidence level. Post hoc comparisons using the Tukey honestly significant difference tests indicated that the mean effluent total phosphorus concentrations with alum and polyaluminum chloride were significantly different than the mean effluent total phosphorus concentration with ferric. Regardless of the difference in total phosphorus concentrations with different coagulants, any of these coagulants could be used at Fond du Lac to achieve the 0.04 milligram per liter effluent total phosphorus limit. And that is all I have for this presentation. Thank you very much for listening.